Quantum mechanics has 5 postulates in, for example, the book of quantum mechanics written by Zetley and several other references. And first of them is that for every state of a physical system, there is a state vector. Now, you can simplify that into saying that for every particle there is a wave function, or even you can say that every particle is a wave. But these will be simplified version in the in the original version of the postulate you don't have the word particle, you have the word state, and that is a better word. For example, in a hydrogen atom you can have ground state or first excited state, both states of electron. So if you say a particle, that is not accurate word. The particle may be in this first state, ground state, or particle may be in first excited state. And the postulate one says that if the state is different, even if the particle is same, you will have a different state vector. So that's one lesson. And the other piece of writing here, it is that state vector contains all needed information about the system. So the details of this qualifier is that all information is through all possible wave functions, and state vector is related to all possible wave functions. If you take dot product, like ordinary vector, if you take dot product with I unit vector, you get x component, you get j with y component, and so on. But here I and j, I, j, k are discrete, and here rather than discrete, I have a continuous label which is x, which values are not 1, 2, 3, but it's any real number. If any real number, then it is dot product, but it's in the result you don't have 1, 2, 3, but you have a continuous dependence on x, and if x is position, that's a position wave function. And if it's a two-dimensional position, you have a position is labeled by x and y rather than only x. It's two-dimensional wave function. Okay, and I'm so far in telling dimension, I'm talking about only position variables count. Another thing which is written maybe newly here is that this is time dependent. So that maybe I have to explain that. You may be new for you. The state vector may be time dependent. If it is time dependent, that means all possible related wave functions with it will become time dependent. So that I did not count when I was telling you dimension. The time is another thing. So that's written here, although it was a bit of understood previously, but written here explicitly that, and I now repeat on that if a vector is time dependent, all possible related wave functions become time dependent. For example, this may be position wave function, real part, that becomes time dependent, because only real part you can make a graph. Wave function in general is a complex number. So far I have talked about position wave function. That's not the only possibility. If a vector changes, then it's multiplied with k. H bar k is according to de Broglie principle, or de Broglie you can say, is momentum. De Broglie says that you multiply with h bar with k is wave number, multiply with h bar, that's momentum. So it's a momentum wave function. So if state vector changes, position wave function, momentum wave function, or momentum wave function, you can use the word phi, and so everything changes, everything, all possible information. So that is the postulate number 1. And the postulate number 1, the next postulate, you can expect what would be next postulate, and that is that if you have information, you have to use that information to predict something. So here the postulate 2 starts, that if you have to predict you have to predict measurable value of a quantity which is called observable. Observable may be observable by a naked eye, or it may be through an operator, whatever it is. If there is a quantity whose value quantum mechanics has to predict, then your first job is to make an operator for that quantity. An operator must be Hermitian. But if you follow the procedure I'm going to tell you, and the procedure tell you, then the operator will be automatically Hermitian, don't bother. And the procedure which I have been telling is that now this course is non-relativistic quantum mechanics, but the same lesson will be for relativistic, but for the moment we remain limited to non-relativistic. Newtonian mechanics. If you have to find, if your target is to find operator for some new quantity, sorry, the word new I am telling you because I am supposing that you know position operator, which is, and you know momentum operator. Momentum is minus iota h bar d by dx in one dimension. So that you know, and you have to find operator for some other quantity. Then what you have to do is find the relationship between two quantities, one known to you, this may be position or momentum, and the new to you. The new is shown by red. Find the relation in Newtonian mechanics or other versions of classical mechanics, maybe if it is non-relativistic quantum mechanics, then Lagrangian or Hamiltonian. And then the same relation between quantities will become relation between corresponding quantum mechanical operators. So an example is that if you know momentum and you have to predict energy eigenvalue, then make energy operator. No, rather than energy, I have written the letter H. Now H stands for Hamiltonian. Now the benefit of the word Hamiltonian rather than energy is that even in classical mechanics, Hamiltonian is a, you have to remember complete definition. Some students say that Hamiltonian is total energy. That is a half definition even in classical mechanics. The full definition is that Hamiltonian is, wait for the end of sentence, listen to the complete sentence, don't cut in the middle. So I repeat, I say now, listen fully. Hamiltonian is total energy, kinetic energy plus potential energy in terms of position and momentum. The second part is also compulsory if you have to define Hamiltonian in classical mechanics. So in terms of position and momentum. Now in going to quantum mechanics, the advantage of Hamiltonian is that you have a momentum. So we know what is momentum operator. If we had we used half mv square in terms of velocity, then we do not know what is velocity operator. So you know momentum operator, the same relationship as in classical mechanics is used between quantum mechanical operator. And once you know that, then rest is nothing new. Is that in position, momentum becomes minus iota bar del, iota h bar del. Momentum square is minus h bar square del square. The square is taken in the sense of operator and then again operator. So first derivative and again first derivative, that is second derivative. And divided by 2m, and position doesn't change. So position remains position if you are using position wave functions. So now we have made the preparation. Whatever we have to predict, we have mathematically preparation. In that we have the operator, and what to do with the operator, that's the question, and the answer is next postulate. And that is that if you know operator, mathematically find its eigen function and eigenvalue, eigenvector or eigenvalue, whatever. First thing is, whatever we find eigenfunction or eigenvector or eigen column is the word is coming maybe later in the course. But whatever way you find it, you will find eigenvalue in any case. And the first thing is eigenvalue in the list of postulates. You remember what we were doing? We had to predict measurable values of a quantity. We found it's the operator of the quantity in the previous postulate, and now if you find eigenvalue, that is what we were after. That means that is our prediction for the measurable values of that quantity, and you can tell experimentalist, please find that that is the value you will appear in your apparatus, and that is the prediction. And such a large number of such predictions have been verified for quantum mechanics, and so far there is no violation. So that's why quantum mechanics is a very good theory so far. Now, what additional comment I can make on this, or maybe with an example, all this is that for example, if your state is a linear combination of electron in hydrogen atom in linear combination of ground state and first excited state. Now the ground state label are 3, maybe, sorry, you cannot read it, you cannot see it because it's written in a very small font, so I speak out for you. The ground state label are 200, and pay attention to the middle one, 200. Middle was 0, and the first exercise said 210, and the middle is 210. The middle is 1. So state has is the linear combination of two possibilities. Middle is 0 or middle is 1. If you measure, you will find one of the eigenvalue, not both. Either middle is 0 or middle is 1. You will find 0 or 1, not both. If you find 0, that means not only the value will be 0, the whole wave function will collapse to 0th wave function, psi 0. And if you measure 1, if your measurement gives you 1, and that is the main problem with quantum mechanics, you cannot tell what will appear, you cannot predict. Whatever it is, you will have to accept it. And if 1 has appeared, you will have to accept it, and then that much is incompleteness of quantum mechanics, very famous incompleteness. That wave function collapses. But next is not incomplete, next is stored by quantum mechanics. If it has collapsed to 1, then the whole state will collapse to 1. So only one of them you will measure, not both. Now that's postulate 3, and now we should be preparing for postulate 4, and the preparation to postulate 4 is that these are possibilities, either 0 or 1. Now every possibility has a probability, and that's with probability this course has started. So this what the probabilities are in postulate 4, and that I have split into two parts, postulate 4a, and then next slide is postulate 4b. And the difference is that in 4a you have non-degenerate probabilities, and 4b you have degenerate. Now I tell you meaning of non-degenerate and degenerate later, because that's something new. Before that, I write something which is, you can say, not new to you, but only generalization of what is you already know. Generalized form is new, but the old form is not new. And by old means the very first occasion I started this course, and that is that position probability density is equal to wave function square. Now postulate is not only for position, postulate for any measurable quantity. So that means it's not, we should not be limited to x. We can have any measurable quantity, but so far generalize it, but not fully. What I mean to mean that any quantity should be continuous. If it is not continuous, I tell you later. If it is continuous, then it is the same equation, and that I told you already before, this equation. And if you need me pointing out, then I point out the old thing, and then I generalize. What I point out in the old thing is that I think it's a few minutes ago I've spoken only the word wave function, but I wrote that if I did not speak, I do it now. And that form is necessary because in postulate 1 I did not speak wave function, I spoke wave vector. So you should know how this wave function is related to wave vector, and that is just like a wave function is a component and wave vector is a vector. You take its dot product of a vector with that, and get, that is component type, and that is wave function. All that is not new to you, but new is that you can generalize to any continuous quantity. Just in that case, rather than x, you have any continuous letter a. Now that will give you probability or probability density, and the answer is probability density. And you might be thinking, why not probability? And the answer is that if you like sticking to the old quantity of position, I speak in that term, and the same will be valid for any continuous quantity, is that, for example, position, even if it is start and end of position are discrete, maybe a position is from 1 to 6. Between 1 and 6, there are how many possible values of x? Don't be limited to integers. It's not only 1, 2, 3, 4. Between 1 and 2, there is 1, after 1 is 1.1. But it's not only. Between 1 and 1.1, there is 1 and 1.001. And not only that, between 1 and 1.001, you have 1.0001. So you can say there are infinite possible values of real numbers between, in any interval. So if you had 6 values, the probability of each value would be 1 over 6. But if you have infinite number of values, then probability of each value will become 1 over infinity, because 0. Now that is not any useful information about a science. We are not doing math. We have to do. So science should be able to tell some information about case to case. If it is not, if it is always 0, that's not any useful information. So case to case non-zero changing is only probability density. And if your prediction is for probability, then you should recall how to convert probability density to probability. And if you need not go back to this course, any previous video, and you just think of that. If you know mass density, if you find mass, what do? You multiply, or in general you integrate. So similarly for probability density, you integrate and with respect to position, and you get probability. So that is all for continuous. Now for discrete, logically it's easier because you don't need probability density. You can directly tell probability, and that is this way, that in discrete case your physical prediction has to be countable. Now is a discrete. So for a count, I can count maybe an integer n, and you will have now countable first value a1, second value a2, and every value has a probability, not probability density. Now that's a question, and you know it can have a non-zero answer. So that's the question, what is probability? And the answer is maybe nothing new, or maybe a slight change which you had to adjust. Psi cat is same as in continuous as in discrete. Now in bra, what you have to take dot product, something new appears. Here you had in continuous you had eigenvalue a, and eigenvector was labeled by the same. In discrete, eigenvalue is an, but eigenvector is labeled by the same n, but the name changes. And why name changes, I can show you here. is that this time in continuous case you had eigenvalue and the same was used as a label for eigenvector. In discrete we can have the same thing is maintained, and both have n, but the name of eigenvalue is a, and the name of eigenvector is traditionally psi n. But if you, that's all the change. Otherwise, is as in continuous case, and continuous is old case. So you have a, and rather than a, you have psi n, nothing else, and you get this time probability. So that's all for probabilities and probability densities. And now I have to compensate, which I have been postponing now, and that is about degenerate. Non-degenerate here. So non-degenerate definition, and that's new to you, listen carefully. Non-degenerate eigenvalue means that for one eigenvalue you have one state. If eigenvalue is third, the state is also third. Same as continuous, as well as same as in discrete. So hopefully you can guess what will be the definition of degenerate. That means, have you done? For degenerate, one eigenvalue can have more than one eigenstate. Eigenstate is another name for eigenvector, you can say. So you have more than one eigenvector. And that all that is written here, and I have written it much together, because here I am doing two things in this slide. One is that I am completing the definition of non-degenerate, degenerate dichotomy. First I wrote non-degenerate and now I write degenerate. And with that I am introducing also another word which is distinguishable, because you need combining both to get something useful prediction. So I tell you, distinguishable is not a new word, that's a traditional English word. So I hope I don't need spending time on it. So the word distinguishable means that if you are making experiment and you repeat experiment many times, then you say this possibility appeared, you can count this time that possibility, maybe this time 4, and you again repeat it, and what appeared you can distinguish. There is the experimental way of telling this time 8, you repeated it, this time maybe 2, and so. So you have a count, how many times 5 appears, how many times 8 appears, how many times 3 appears. Now the combined probability would be in how it will be calculated. If that's the question, the answer can start with an example. That if your experiment is maybe simpler, start with not quantum, just simply classical dice, and rather than here first substate, second substate, third substate, you can say substate, or your state is even. Dice may show an even number or dice may show odd. So your state is even or odd, that is n. N can be even or odd, and your substate for one state and for one eigenvalue, you know, many substate. If your state is even, your substate can be details of even maybe 2, 4 or 6. Now in that case, dice, in case of dice, what appear? You can distinguish. After I throw a dice, you can tell it's 4 appear or 6 appears or 2 appears. Now you can count how many times 2 appeared, how many times 4 appeared, how many 6 times 6 appeared. And you know, whatever it is, the 4 appeared or 6 appeared or 4 appeared, it was that even appeared. So the count of even is the count of 2 plus count of 4 plus count of 6. Now coming to quantum mechanics case, one thing I can repeat what I have said it here, that for this state labeled by n, your substate may be what I said 6, So count of 6, your substrate may be 7, count of 7, your substrate may be 8, count of 7, and this is distinguishable. You can add up counts, like you add up count of 2, 4, 6. Another example, and then I tell the rule. First I mention the third example, explain to third example, and then I tell the rule. The third example of countable could be that hydrogen atom, if you have your state is, before measurement, remember, is a linear combination of 3 states. First substate, second substate, and third substate. I am counting as sub because these all correspond to second state. Second state means second energy of hydrogen atom. So you remember the 3 examples I've shown you here. One is just mathematical, the sum is dice, one hydrogen. In any case, for one quantity you can have many sub quantities. Sub quantities means sub count. So this was the problem, and now the question is, what is the quantum mechanical rule for that, for all 3 examples? And so sorry, the dice is not quantum, but still the first and third are quantum. And in case the quantum mechanical rule, now I've been so far telling the question, and the answer answer I tell you how to calculate probability, and the answer is that when you counts add, your probabilities also add. So you first calculate probabilities for every substate, and then you, by squaring you get probability, and then you sum, and the sum is will give you total probability of the main state, because these are the all substate count added up. Now the counts are approximately same as probabilities. For example, in dice, if you have all sides counts are same, underlying the reason is that probabilities are same. So counts are approximately probabilities. If your counts add up, your probabilities square sum, they add up. And because every sub possibility meant a possibility for the same an, so the total sum will be probability of the state an. So that's all for postulate 4, and that was the lengthiest of probabilities, sometime probability density. With that, before going to postulate 5, I would very much like to tell you a lesson which is very important lesson, so much important lesson that even I'm interrupting in a way a postulate to tell you that, because maybe there's no other place in the course to tell you that, and that main lesson, one of the main lessons of quantum mechanics, and that is the word distinguishable. I said it's an English word, but its usage in quantum mechanics is new to you. So far, when he said you can label each count separately, you can, and then you can add up counts, and then that means you can add up probabilities. That is for distinguishable. If you can tag the label, but if you cannot tag, like in double slit experiment, you cannot. In double slit experiment, you have on the detecting screen, you sometime you have one dot, second dot, third dot, and you cannot tag. There is no way of knowing. If in experiment there is no way of knowing that this dot was because of slit 1 or because of slit 2 and so on, then you cannot tag. You cannot add probabilities. In that case, you have to first sum to find total wave function and then square. So non-distinguishable, you have to first sum and then square, and for distinguishable, you have to first square to get probability and then sum. So that's the main lesson, one of the main lessons of quantum mechanics, and try to remember this always. That's all for 4th postulate and a side lesson, and now we are ready for 5th postulate, and that is that time dependent Schrodinger equation. So time dependent Schrodinger equation is essentially telling you that energy operator is this. So if you are a bit surprised, you don't recall what is the word energy of what is the operator, then I remind you. So far we have been I have told you momentum operator, and the way I introduced momentum operator was that if you take a plane wave and you apply that operator and you get eigenvalues as momentum. So I hope you have reminded yourself the word operator and how it was introduced. Now make a slight change. Rather than x, you take t. Your differentiation essentially unchanged except for a sign change minus. To compensate it here, you make a sign change as well. So its differentiation should be simple. You do it and you get exponential unchanged, and minus iota omega is from that power, and you multiply with iota h bar, you get h bar omega. Now h bar omega is E. So this is apparently you can say proof, but it's not. It's only a reminder, not proof, because I have shown calculation for a plane wave, and a general quantum mechanical wave function is not always plane wave. So that is just a memory trick, not a general rule. Because this is only plane wave, the general rule is not proved, but that is a postulate, and that's the fifth and last postulate here, and that is there, that your energy operator is that is nothing new. Maybe for you, if you are not very attentive, then it may turn out to be new to you, that rather than I spoke energy operator but wrote the letter H. I think the reason is that H stands for Hamiltonian, and Hamiltonian energy operator, the word Hamiltonian reminds us that we have to express energy in terms of momentum, and the benefit of in quantum mechanics is that for momentum we know expression with position wave function, namely I minus iota h bar del. So you take momentum square, and that I have already written in postulate 2 slide 3. So right hand side was not new, the left hand side is new, and that is energy operator, and that's all I have in this lecture. And now by the way of summarizing it, I give an alternative expression for 5 postulates, and that alternate expression is one sentence. You can if you memorize one sentence, if you remember one sentence, then I think my effort is that you will remember all 5 postulates apart from mathematical details. So one sentence can replace with your understanding, they can replace all 5 postulates, and I postulates means in a way you can summarize the whole quantum mechanics. Anyway, the sentence is that for every measurable quantity you find an operator. That was postulate 2 here. And then you remember what we do with the operator. You find its eigenvalue, and that is our prediction for the quantity to tell to experimentalist, and that eigenvalue is prediction for the quantity, and that was postulate 3 here. Sentence is not complete because there was postulate 4 as well, and that postulate 4 tell you that when with eigenvalue you will find eigenfunction, and eigenfunction, you square eigenfunction, that gives you probability or probability density. So that's all for 5 postulate. And the 5th was there because when you say eigenfunction, how to find eigenfunction, the answer is that you solve the differential equation called Schrodinger equation, and that's the most common answer, and that completes this all 5 postulate. Thank you for watching, and don't forget to subscribe to this channel.